So, good evening, everyone. So today is the 8th week of our lecture. So, today we are going to discuss problems on the modes of convergence. So before that, in the last lecture I didn't discuss two of the problems. So today I'm going to first take the first problem, which we didn't consider in the last session. So this was the problem. So it was given that x and y are IID random variables, and we need to prove that expectation of x upon x plus y is equal to expectation of x upon expectation of x plus y. So let's take x and y as uniform distribution from 0 to 1. So this is asked it is asked that if this statement is true for all the x and y which are IID, which are independent and identically distributed. So we are taking a uniform distribution. We are taking x and y as a uniform distribution for 0 to 1. So we want to see like whether it is true for this basic example or not. So this expectation of x is nothing but it is 1, and expectation of x plus y is equal to expectation of x plus expectation of y, as x and y are independent. So this will be 2. So this RHS will become 1 by 2. Now we need to calculate the LHS. LHS is expectation of x plus y. Now this expectation can be calculated by x upon x plus y fxy x comma y dx dy, right? This will be 0 to 1, this will be 0 to 1. Okay, so from the definition of expectation, but we know that x and y are independent, so this will be nothing but fx into fy. So this will become x plus y fx fy dx dy 0 to 1, 0 to 1. So when you solve this thing, this fx and fy are nothing but 1, because x and y are uniform distribution, so this will be 1. So this will become x upon x plus y dx dy 0 to 1, 0 to 1. So we will see that this will come out to be 0. So this LHS value is 0. When you solve it, it will come out to be 0. This LHS is 0, but RHS is, we saw it was 1 by 2. So this is not true. So this statement is not necessarily true for IID random variables. Okay. So I hope this is clear. So today we are going to have a discussion on the topic modes of convergence. So we have discussed different type of random variables. We have then seen that in some questions we need to rely on two or more random variables. So we have seen how to calculate the this joint probability distribution for two random variables, and how to uh, calculate the conditional probabilities for two random variables. And now we will see the distribution, not the distribution, but how a sequence of random variables will converges or not. Okay, of four modes of convergence which is considered in this study. So I will quickly go through all those four concepts and then we will walk to the questions. So first is convergence in distribution. So a random let's suppose there is a sequence of random variable x1 x2 till xn with CDF fx1 fx2 similarly fxn. Okay, so we will say that this xn limit n tends to infinity, this xn converges to some random variable x if limit n tends to infinity fxn is equal to this fx, probability mass function for some x. Okay, if there exists any random variable with CDF fx, and if our CDF of this xn converges to that function, then we can say that our sequence of random variable will be converges to random variable x with a converges in distribution. And this is how we represent the convergence in distribution. Okay, so when we solve some problems, then you will understand it more better. Second is convergence in probability. So it is like that this sum xn will converge to x, and this is the sign that it will converge in the probability if there exists some epsilon greater than 0 such that the probability that xn minus x is greater than epsilon is equal to 0. Just a minute. So what it is saying that this is the sequence of random variables and this is the sum x. So if the difference between them is greater than some small epsilon value, and the probability that this difference is greater than some small epsilon value is 0, which means that there is no difference between xn and x, then we will say that our sequence xn will converge in probability to some random variable capital X. So this is convergence in probability. Third is convergence in earth movement. So we will consider some sequence of random variable such that the expectation of xn in this R is a finite quantity. Okay, this expectation in earth moment will exist. Then we can say that if limit n tends to infinity, here also the limit is n tends to infinity. So the limit n tends to infinity, if this expectation xn minus x in the earth moment is equal to 0, then we will say that xn will converges to some x in the earth moment. Okay. So now moving to this last convergence, which is convergence is almost surely. So this is when the probability that limit n tends to infinity, this xn is equal to x with probability 1, then we will say this xn will converges to x absolute surely, almost surely. Okay. Here we are not taking any epsilon or some difference, we are just saying that xn will be exactly equal to this capital X and the probability of this is 1, then we can say that it is convergence is almost surely. Okay. So now there is some dependence. So if xn converges to x within a probability is a probability based convergence, then it will converges with some distribution also. It implies that, but it does not work in a converse way. Okay, similarly if xn is x with some with first moment with the expectation, then we can say that it will also converges through probability. If xn converges with rth moment, this implies that xn will converge to r in r minus 1, in r minus 2 till up to first moment of first moment of convergence. And last is that if xn is almost surely converges to x, this means that this implies that xn will converge to x with some probability. Okay, so this absolute surely, almost surely implies to this implies to this. Okay, similarly this implies to this implies to this. So all of these are little connected, but this distribution based is not so connected. So we can make a graph like this. these both implies that xn converges to with probability, and this implies that xn will converges to x within some distribution. This is first moment. Okay, so this is an important chart. So now moving on to this weak law of large number. So here this it is said that the probability that some x1 plus x2 plus xn minus mu is greater than epsilon is less than equal to, where x1, x2, xn are IIDs. Okay, and epsilon is greater than 0, and this all these xi's has mu as mean and this sigma square is variance. Then this holds. Also this probable when limit for limit n tends to infinity, this probability of this x1, x2, sum of this sequence minus mu is greater than epsilon is equal to 0. This means that this x1 plus x2 plus xn will converges to mu within some probability. So this is weak law of large number. Okay, and if limit if probability that limit n tends to infinity x1 plus x2 plus xn divided by n is equal to mu is equal to 1, that this is almost equal to mu, that it will exactly equal to mu, and the probability is 1, then we can say this x1 plus xn almost surely. So this is known as strong law of large number. So here difference is that there is some epsilon which is a positive quantity where epsilon is greater than 0, it's strictly greater is equal to 0. Okay, so this difference will be very very small. This is not equal to 0, this will be very very small, but here the difference will be exactly 0. So therefore this is strong and this is a weak property. Now we define the central limit theorem. So let omega f and p defines a probability space, be a probability space. Let x1 x2 xn be a sequence of IID random variables defined on this probability space. Now assume that expectation of all these random variables is mu and variance of all these is sigma square, which is greater than 0 for all I 1 2 3 and n. Okay, then we define a Zn, which is nothing but this sum of I from 1 to n minus expectation of these values divided by variance of sum of these values. Okay, the Zn is defined in this way. Then for large n Zn is approximately a standard normal distribution. This is central limit theorem. Okay, so now we will try to solve few questions based on these concepts. So I will write the question and then we will solve it. So let's suppose there are 100 men on a plane. Okay, xi be the weight of ith man. ठीक है, xi denotes the weight of ith man and xi's are IID random variable and this expectation of xi is 170 and sigma is 30. Okay, now we need to find the probability that the total weight of the men on plane is greater than 18,000 pounds. So we need to find the probability that total weight of men on plane is greater than 1800. So let's take a W, which denotes the sum of weight of all the 100 people. Okay, now this expectation of W is nothing but expectation of x1 plus expectation of x2 plus expectation of x100. As these are all independent random variables, x1 x2 and x100 are independent of each other. That's why we are taking the expectation for whole W will be sum of separate individual expectation of each random variable. So this will be 100 into expectation of xi is 170. So this is 17,000. Similarly, variance of W will be 100 into variance of xi. So this will be variance. So this will be 100 into 30 into 30. As this is sigma and variance is sigma square. That's why we took 30 into 30. So this is 90,000. So we have average is 17, expectation of W is 17,000, variance of W is 90,000. Okay, so sigma of W will be 300. So we need to find the probability that this W should exceed 18,000. So from using this central limit theorem, we say that this W minus 17,000 divided by 300 is greater than 18,000 minus 17,000 upon 300. We need to find this probability. So this is probability is greater than, this will be 1000 divided by 300, so this will be 10 by 3. So I erase that. So we know that for this from central limit theorem, we know that this W is a standard normal distribution. Okay, not this W, but this thing. Okay, for large value of n here is 100. So this is a large number. N is 100. So this is a standard normal distribution. So this we can denote this as some Zn. So the probability that Zn is greater than 10 by 3 is nothing but the 1 minus probability that Zn in, I will write it on next page. So using CLT we can this W, which is sum of this 100 with expectation of 17,000 and deviation of 300. So for as n equal to 100, large quantity, so we can define some Zn which is a standard normal distribution. And which can be written as this sum of xi's minus mu of expectation of W upon sigma of W. Okay, so this is Zn. So the probability that the Zn is greater than some quantity, and that quantity is so we need to find that probability that W is greater than 18,000. So we can do some changes in both the side. So this will be EW upon sigma. Similarly, we will do it on the LHS on this RHS side. So this is same. We did these changes on both sides. Now this we know from central limit theorem is a standard normal distribution. So this probability becomes Z greater than 10 by 3, which is nothing but 1 minus probability that z is less than 10 by 3. So this is nothing but 1 minus psi of 10 by 3. We discussed this in when we talked about normal distribution and standard normal distribution. What is this phi? And using that chart of phi, we can calculate the value of psi 10 by 3, and this will come out approximately 4.3 into 10 to the power minus 4. Okay. So this is the way in which we can use the central limit theorem concepts for the real application. So the probability that the sum of weight of all the men on board will exceed 18,000 pound is this 4.3 into 10 to the power minus 4, which is very low. Okay, I hope this is clear. Now moving on to the second problem. Let x1, x2 till x25 be IIDs. Okay, and we are given the PMF of x's. So if the probability is 0.6 if this k is equal to 1, probability is 0.4 if this k is equal to minus 1, and it is 0 otherwise. So the probability that x will take the value 1 is 0.6, and probability that x will take the value minus 1 is 0.4, and otherwise it is 0. Now let y is equal to x1 plus x2 plus x till x25. Now we need to find the probability that this y is between 4 and 6. What is the probability that the value of y is between 4 and 6? Okay, we need to find this probability. So first we will find the expectation of xi. So here you can see that we need to use limit theorem. Okay, because there is sum of some random variable, so we use the central limit theorem concept. So that for that we need expectations. So first we will find the expectation of xi's. So it will be 0.6 into 1 plus 0.4 into minus 1. This will be 0.2. Then we need to find this variance of xi. This will be 0.6 into 1 into 1 plus 0.4 into minus 1 into minus 1. So this will be this is the expectation of xi square. This is 0.6 into 1 into 1 plus 0.4 into minus 1 into minus 1. So this is 1. So variance of xi is expectation of xy square minus expectation of xi whole square. This is 1 minus 0.04. This is 0.96. Okay, this variance is 0.96. Now we will find the expectation of y, which is nothing but expectation of x1 to x25. As these are independent, this will be expectation of x1 plus expectation of x2, expectation of 25. This we find that expectation of x1s are 0.2, so this is 0.2 into 25, so this will be 5. Similarly, variance of y is variance of x1, x2 till x25. So as all of these are what? Independent, this will be x1 plus x2 plus x25. So this is 25 into 0.96. Okay, so this will come out to be 24. Okay, so from variance of y is 24, so the sigma of y is root over variance of y, which is root 24. We can write it as 2 root 6. Now we need to find this probability of y is between 4 to 6. So we know that we can, from central limit theorem, we can change it, we can do some alterations, which will be 4 . So what, from central limit theorem, what we know? So we know that this summation 25 minus this expectation of y divided by sigma y, this is a standard normal distribution, and we can find the probability for a standard normal distribution. So we are asked that probability that y is between this, we can change it and write it like this. We did some alteration on all the sides, so this will be nothing but 4 minus expectation of y is 5 and sigma y is 2 root 6. This I can write some z. This is 6 minus 5 by 2 root 6. So this will be the probability that z is in range of minus 1 upon 2 root 6 to 1 upon 2 root 6. So this is nothing but psi of 1 upon 2 root 6 minus psi of minus 1 upon 2 root 6. So from the chart of that psi we can find these values, and we will get that this probability that y ranges from 4 to 6 is nearly 0.2405. Okay. So with the help of this central limit theorem, we can find the probability of such such sequences very easily, because we are converting them into a standard normal distribution, and to find the probability for a for a random variable that is standard normal distribution is very easy. Okay, now we'll move on to the next question. So I will write the question first. So let's suppose you have 64 guests at a party. And you need to make sandwiches for the guests. And you guess that one guest will eat either 0, 1 or 2 sandwiches with probability eat 0, 1, 2, 1 by 4, 1 by 2, 1 by 4. Okay. And number of sandwiches each guest eats are independent of the number of sandwiches other guests are eating. Okay. So now the question is, how many sandwiches you should make so you are 95% sure that there is no shortage. So let's see what is happening here. We have a party and we have 64 guests at the party. Now each guest will eat 0 sandwiches with probability 1 by 4. He or she will eat 1 sandwich with probability 1 by 2, and he or she will eat 2 sandwiches with probability 1 by 4. Now the number of sandwiches which a guest is eating is independent of the number of sandwiches that other guests are eating. Okay. Now we need to know how many sandwiches we want to make to ensure that there will be no shortage with the probability of 95%. So let's suppose x1 denotes number of sandwich eaten by guest number 1. We will assign number to each guest. So there will be 64 guests, so we will assign 64 numbers. So x1 denotes the number of sandwich guest number 1 eat. Similarly, x2 is the number of sandwich guest number 2 will eat. Okay, similarly there will be x64. Now we can see and this is given that x1, x2 till x64 are independent of each other. And we are given that this x1, all these xi's will eat 0, 1 or 2. This is with the probability 1 by 4. This is with the probability 1 by 2. This is with the probability 1 by 4. So this is kind of a probability mass function. For these random variable x. Okay, so now let's suppose total number of sandwich these guests will eat is, so y is nothing but x1 plus x2 plus till x64. The total number of sandwiches the guest will eat will be y. Now the question is, what is the probability that this y is this probability should be so we know that we want that there will be no shortage. Okay, so this shortage will only happen when this will be less than the number of sandwiches required. So we want that this probability should be equal to 9.95. Okay, not 95, greater than 0.95, because we want this probability should be greater than 0.95, that there will be no shortage. Okay, so the probability that capital Y is less than equal to small y should be very high. Okay, so now so first we will find the expectation of xi. So this will be 0 into 1 by 4 plus 1 into 1 by 2 plus 2 into 1 by 4. This is 1 by 2 plus 1 by 2, which is equal to 1. Similarly, we will find the second moment of expectation, which is 0 square into 1 by 4 plus 1 square into 1 by 2 plus 2 square into 1 by 4. This is 1 by 2 plus 1, which is equal to 3 by 2. So variance of xi is expectation of xi square minus expectation of xi whole square. This is 3 by 2 minus 1, which is 1 by 2. So we find that this expectation of xi is 1 and variance of xi is 1 by 2. Okay. Now y is summation of xi's from I equal to 1 to 64. Expectation of y is expectation of sigma I equal to 1 to 64 xi. This is nothing but the summation will come outside and this will like this. This will be 64 into 1, which is 64. Similarly, variance of y is 64 into 1 by 2, which is 32. Okay. So this will give sigma y as 4 root 2. So now we want that this probability should be at least 0.95, and we can convert this into a standard, as we know that this is using central limit theorem. Sigma y less than equal to y minus epsilon y sigma y greater than equal to 0.95. So um, this is nothing but y minus expectation of y upon epsilon y. And this should be greater than equal to 0.95. है ना? So from this phi chart we can get this value, that at which x this is equal to 0.95. So we can find this x. So this will come out to be 1.6449. okay, this x is nothing but psi inverse of 0.95. so from the chart we can see this x come out to be 1.6449. this is nothing but small y minus expectation of y upon sigma y. Here this small y is number of sandwich we make. Okay, so what are we finding? The probability, this is the sum of sandwich guest will eat. This is what we plan to make, and we want this probability should be 0.95, that we will make more than this, the sandwiches the people will eat, then only we will not go under any shortage. Okay, so we found that this value from central limit theorem, we find that this y minus ey sigma y minus expectation y upon sigma y should be greater than 0.095. This is nothing but psi of y minus expectation of y sigma y. So this y minus expectation y upon sigma y should be greater than equal to phi inverse of 0.95. This is 1.6449. So this y minus this expectation of y is 64. The sigma is 4 root 2, 0.6449. So from here we get that this value comes around to be, should be 73.3. So y is 74. So we need to make 74 sandwiches, so that there will be a 95% surety that we won't go under any shortage. Okay, so this is for the number of sandwiches. Similarly, you can do it for this number of benches needed in class. Okay, so there is some probability that student will come and student won't come to the class. According to that, we can plan the sitting area. Okay, in the sitting area will be this. For the classroom it is a little difficult, because if all the students come someday, then we need to arrange it to the maximum capacity. But like the mess area, if we want to see the capacity of a mess, then we need to see how many people are arriving in each time interval, and then we can take that sum of all the in any time period how many people are coming, and then we can make some arrangements like that, that we won't go under any like that the mess will become full. Okay, so like this question is, I added this question because I want to show the real life implications of this central limit theorem, that why it is important. So in the aeroplanes, the plane there are some food and tea, coffee options in the plane. So there they need to make decision how many sandwiches they need to pack, how many other kind of products they need to pack, and they will do it using the probability that how many people are going to purchase a coffee, what is the probability that people are going to purchase a coffee, the people who are traveling. So according, based on that probability, they will find the number of coffees they will uh, they will take for their journey, because they cannot take as much as possible, because there is some restricted capacity in the aeroplane. So in that they need to make decision how many of each items they need to carry. So these all decisions are made using such type of these type of concepts. Okay, I hope this is clear. So moving to the next question. So I will add all these questions in the presentation file. So so I will add it after the class. So let these x1, x2, xn are IID exponential random variable with parameter lambda, where lambda is equal to 1. Now suppose this x bar is equal to x1 plus x2 plus xn divided by n. We need to calculate how large should be the n such that the probability that this summation will lie with x bar will lie between 0.9 to 1.1 is greater than equal to 0.94. Just a minute. Okay, so we are given that there is some sequence of independent identically distributed random variables. All of these random variables have an exponential distribution with lambda equals to 1. We are given that x bar is this x1 plus x2 till xn divided by n. This is also known as sample mean. So we need to find that how much large should be the value, this value n, so that this the probability that this x bar falls into 0.9 to 1.1 is greater than 0.95. Okay, so we know that we can see that there is something CLT here. So in CLT, what is the thing? That this summation of xi's minus expectation of summation of xi's divided by this sigma of summation of xi's is a standard normal distribution. So we need to do something like that. So let some y is equal to x1 plus x2 plus xn. This x bar is nothing but this y by n. Okay, now these expectation of xi is 1 by lambda and variance of xi is 1 upon lambda square, as they are exponentially distributed. Expectation of y will be n by lambda and variance of y will be n upon lambda square, right? Lambda is equal to 1, so expectation of y is 1 and variance of y is, this is n, and variance of y is also n. Now we need to find the probability that this x bar is between this. This is nothing but this y by n is between 0.9 to 1.1. So we need to find the probability that this y lies between 0.9n to 1.1n. Now we know what we want to do. We can write this as minus expectation of y sigma y, this y minus expectation of y sigma y 1.1 and minus expectation of y sigma y. This is standard normal distribution and we can find this is 0.9 n minus n upon n. This I am taking as z. This is 1.1 n minus n upon n. So we need, this is minus 0.1 to 0.1. So this is nothing but psi at 0.1 minus psi at minus 0.1. So from the chart we can find these values and this will come out to be okay, so we need to the question was this should be greater than 0.95. So this should be this should be greater than this 0.1 minus 0.1. This should be greater than 0.95. Okay, or I am doing something wrong. Okay. So the sigma y is not n, it is root n, right? So this will become point, this is root n and this is also, here also it is root n. I will rewrite it again. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So we found that this expectation is n, variance is n. So this sigma is root n. So here this will be probability of minus 0.1 into root n is 0.1 root n. This is the probability. This should be 0.95. So we can move it there. And we can get that this psi minus 0.1 root n, no 0.1 root n minus psi 0 minus root n is nothing but 0 should be greater than equal to 0.95. So we will see that this 2 into 0.1, okay. So this is the property of this psi function, that rho of minus x is 1 minus psi of minus x is 1 minus psi x. So we can write it as 2 of psi 0.1 root n minus 1. Okay, this is written in this way. We wrote this term as this will become this, which is greater than or equal to 0.95. So from here we will see that this (1.95) should be greater than 0.975. So 0.1 root n should be greater than sine inverse 0.975. So from the chart we will get this value, and this is 19.6. So this root n is equal, should be greater than equal to (196). So this will be 1.96 and this will be 19.6. So n should be greater than 384.16. So n should be equal to 385. So when n is equal to 385, we will conclude that this exponentially distributed random variables, the sample mean will lie between 0.9 to 1.1 with probability 0.95. Okay. Now we will move to the next. So now we will try to see few questions on this convergence part. So these will be theoretical based questions because I need to see, I need you to know that I want to explain how these problems can be solved. how how are the questions on the topic of this convergence type of problems. What are the type of questions are asked on on the topic of this convergence? Okay, so this example, let x1 x2 till xn be a sequence such that xn is a geometric distribution with this lambda by n parameter for n equal to 1, 2 and so on, and lambda is great. This lambda is greater than 0. Okay, it is a constant. Lambda is a constant value. Okay, so now we will define a new sequence yn such that yn is equal to xn upon n. Okay, now we need to show that this yn converges in distribution to exponential distribution with parameter lambda. Okay, so this is the question. We are given a sequence of random variable, and all these random variables are geometric distribution with parameter lambda by n, where lambda is a constant and n will be changed. For x1 it is 1, for x2 it is 2, for xn it is lambda by n. Now we define a new random variable yn which is equal to xn by n. Okay, now we need to show that this yn converges in distribution to exponential with exponential random variable with parameter lambda. Okay, so we need to show that this yn converges to some y where y is a exponential distribution, is a exponential random variable with parameter lambda. Okay, so note that let's W is a geometric distribution with some p, then the probability that this W is less than equal to some value L is equal to summation k equal to 1 to L 1 minus p into to the power k minus L into p. So this will come, p will come out, this will be 1 minus p k minus L. So this is nothing but 1 minus p to the power L. This will come out in this sense. Now this yn is xn by n. Okay, now the probability that yn is less than equal to y is probability that xn by x is less than equal to y. This is the probability that xn is less than equal to yn, right? And we have seen for the geometric probability distribution, this is nothing but this quantity is nothing but 1 minus p to the power n. So this will become 1 minus lambda by n to the power ny. Okay, p is the parameter here, and parameter for our x is lambda by n. So we wrote this 1 minus lambda by n into ny. This is because here this L is an integer value. So that's why we have taken this, the integer value of this n into y. The product of this should be an integer value. Okay. This will be the largest. I will write it here. Largest integer less than or equal to ny. Okay. Now probability is nothing but 1 minus lambda by n ny. This is fy. So for the convergence in distribution, we want this, that when this limit n tends to infinity, this thing converges to something. Okay, now we will find what will be this thing. So this is limit n tends to infinity 1 minus 1 upon lambda by n into ny. Okay. So this limit is for this one. Now this one will come out, and this will be limit n tends to infinity 1 minus lambda by n ny. Okay, so this is nothing but 1 minus e to the power minus lambda y for n tends to infinity. This is this. Okay. So for limit n tends to infinity, fyn is equal to probability distribution function of some let's say some y, where this y is exponential distribution with parameter lambda. Let's do it. So now we will move to the next question. It is a similar kind. Let x1, x2, x3 be a sequence of IID uniform distribution, uniform between 0 to 1. Now we define a sequence yn which is minimum of these numbers. Okay. Now we want to show that this yn will converges to 0 in distribution, in probability, and almost surely, and for any earth moment. We need to show all these for convergence for this sequence, for this yn. So we know that these xi's are uniform between 0 to 1. So this fx is 0 when x is less than 0, x when x is between 0 to 1, and 1 when x is greater than 1. Okay. So now we will find this cumulative density function for yn. So this is probability that yn less than y. Probability that minimum of yn should, okay. Oh boy. We can write this as 1 minus probability that yn is greater than y. Okay. Then we can write this as 1 minus probability that minimum of yn should be greater than equal to small y. So if yn is minimum of x1 till xn. So if minimum value from any sequence is greater than something, then all the values will be greater than something. It will be greater than that thing. So this is 1 minus probability that x1 is greater than y, x2 is greater than y, till xn is greater than y. This is joint probability distribution function for x1, x2, x3 till xn. We know that these are independent. That's why this becomes as 1 minus probability x1 greater than y into probability x2 greater than y into probability x3 greater than y, and so on. This is nothing but 1 minus probability of fx1y. This is 1 minus probability of fx2y, and so on. So this is nothing but 1 minus fx1 for y is y. Similarly, this will become 1 minus fx2 for value y is y till 1 minus y. So this is 1 minus y to the power n. Okay. This is the cumulative density function for y. Okay. Is 1 minus 1 upon y to the power n. Now for n tends to infinity, so limit that n tends to infinity for this yn. Oh, sorry. Well, this was 1 minus y to the power n. So when this n tends to infinity, okay, this tends to infinity. So first I need to define this range of y. So this yn is minimum of this sequence, right? x1, x2, minimum of any of this value, which will be the minimum, that is the value of yn. So we can see that these x1 has range of 0 to 1. Similarly, x2 has range of 0 to 1 till xn has range of 0 to 1. So this y is also range from 0 to 1 only, right? So that's why this value of small y is from 0 to 1. So I will write it here. Range of x1 0 to 1. Range of x2 0 to 1. Range of x1 is equal to 0 to 1. So the yn, which is minimum of x1 till xn, so the range of yn is also 0 to 1. And now we know that this is 1 minus y to the power n, and we know that y ranges from 0 to 1. Okay, so for limit n tends to infinity, what is the value of this function? So for y equal to 0, this will become 0. This will become 1 to the power n. So 1 minus 1 is 0. This will come out to be 0. Okay. If y is less than equal, it will be equal to 0 only. And if this y equal to 1, then this will become 1 minus 1 0, 0 to the power n is 0, this will become 1, this will become 1 if y is greater than 0, right? Because if it will be, let's say this value will be y is, let's suppose y is 0.5, then this 1 minus 0.5 is 0.5, 0.5 to the power infinity. So as this number is less than 1, this will, for this infinitely after infinite time it will become 0. So that's why this will become 1. So this limit n tends to infinity, this function will go to 0 if y is 0, and it will goes to 1 if y is greater than 0. So we can say that yn goes to 0 with some distribution. Now so we found that this cumulative density function for y is, it is 0 for y less than 0. It is 1 minus y to the power n when y is from 0 to 1. It is 1 otherwise. Okay. So for yn goes to 0 in probability, converges to 0 in probability, we need to show that this limit n tends to infinity, probability that this yn is greater than epsilon is equal to 0 for some epsilon greater than 0. Okay. So okay, now we will see what is the probability of yn greater than epsilon. It is 1 minus probability that yn less than equal to epsilon. This we know. Okay, if y is it's a continuous random variable, we can write it as epsilon. So this is nothing but 1 minus, if epsilon is between 0 to 1, okay, this epsilon is between 0 to 1, then this probability yn greater than epsilon becomes 1 minus yn less than equal to epsilon. This is nothing but cumulative density function on epsilon. This is nothing but when this epsilon is between 0 to 1. So if y is 0 to 1, this is 1 minus y to the power n. This will become 1 minus epsilon, 1 minus epsilon to the power n. This is 1 minus 1 plus 1 minus epsilon to the power n. This is 1 minus epsilon to the power n. Okay. So now we can put limit on this. It is limit n tends to infinity for 1 minus epsilon to the power n, where epsilon varies from 0 to 1. So this is nothing but 0. So this limit n tends to infinity, probability that yn, similarly we can show it for this minus yn is greater than 0, so we can say that yn will converges to 0 in probability. Okay. Now we will show it for the rth moment. So we want to show that this rth moment converges to 0. for all r greater than equal to 1. So this yn was 0, 1 minus 1 minus y to the power n and 1, y less than 0, y between 0 to 1 and y greater than 1. So we differentiate it one time. We will get this probability density function. This is nothing. This will be n into n into 1 minus y to the power n minus 1 when 0 otherwise. This is probability density function. Now if we want to find the expectation of yn for any rth moment, it will be nothing but y into r into f(y) dy. It will be 0 to 1, limit is 0 to 1. So 0 to 1 yr n, what was this? 1 minus n minus 1 to the power dy. Okay. So this is n yr 1 minus y to the power n minus 1 dy. So this value, so as r is greater than 1, what we got, this expectation of yn for the rth moment is (0 to 1) n yr 1 minus y to the power n minus 1 into dy. So as r is greater than equal to 1, this is greater than equal to 1, we can write that this thing will be less than equal to ny 1 minus y to the power n minus 1 dy, because y is between 0 to 1. It is between 0 to 1, so the y is between 0 to 1. So for example, let's say y is equal to 0.5. So 0.5 to the power some r, where r is greater than 1, है ना? So let's suppose this r is equal to 2. So 0.5 square is less than 0.5 to the power 1, right? So we are writing that only. So this is equal to this, but this quantity is less than this when we take this r as 1, right? Because y is between 0 to 1, and for such values, when we increase the power, the value will decrease, right? So this is this, and this will be equal to, when we solve it, this will come out to be 1 upon n plus 1. Okay, so this expectation of yn into rth moment is less than equal to 1 upon n plus 1. As limit n tends to infinity, this expectation of y and r is going to be 0, right? Because n going to infinity, 1 upon infinity is 0. So we can say that yn converges to 0 with some rth moment. Okay. Now it is remaining this absolute part. So we remember that this yn greater than epsilon is less than infinity. Sorry. So in the probability part, we saw that this limit n tends to infinity, probability that yn is greater than epsilon is equal to limit n tends to infinity 1 minus epsilon to the power n. And as epsilon was between 0 to 1, we concluded that limit n tends to infinity, probability yn greater than epsilon is equal to 0. Okay. But if we take this probability as summation for n equal to 1 to infinity, this yn, this is nothing but n equal to infinity 1 minus epsilon to the power n. So this is a geometric series. So the series will be 1 minus epsilon upon epsilon. Okay. Now for limit n tends to infinity, this becomes this 1 minus epsilon upon epsilon. And this is less than infinity, right? And epsilon is the value between 0 to 1. So we cannot, this is epsilon is greater than 0 and maybe equal to 1. Okay. So for all values of epsilon, this will be some finite quantity, right? So for this convergence of almost surely, we need that the probability that yn, the probability that limit n tends to infinity, yn is equal to 0 should be equal to 1. Okay. So from this probability part, we had this um, that this limit n tends to infinity, probability that this yn is greater than epsilon is equal to 0. We had this, but we want this thing, right? So I just got confused. Just a minute. Okay. So this thing we know, right? This we know from the probability distribution, probability convergence. Now to show that this yn is 0 almost surely, we need to show that this probability for I equal to 1 to infinity, the probability that this yn should be greater than epsilon should be a finite quantity. Okay, this should be a finite quantity, right? Or the probability that this infinity yn is equal to 1. Okay. So we know that this n equal to 1 to infinity probability yn greater than epsilon is nothing but n to infinity 1 minus epsilon to the power n. So this is 1 upon 1 minus epsilon. Sorry. One minus epsilon upon epsilon. This is a finite quantity. Okay. Therefore, this yn goes to 0 absolute almost surely. Okay, so today I have these many questions. So we will discuss some other concepts in the next class. So if you guys have any doubts, you can ask me in the next class. Okay, so I am ending the session now. Thank you.